Hello, lovely grade 12s. Today we're having a lesson on differentiation of exponential and log functions. If you recall in the previous video that I put up, we were talking about ln and we were talking about the number e, and we first had to go and do that before we could come back to the final section of differentiation, which is the differentiation of that exponential function specifically involving the number e, and the log function specifically involving the ln of x, which is then the inverse of that e to the power of x function. Right, so first things first, we have to talk about the derivative of e to the power of x. Now on your formula sheet, so this one right there is on your information sheet. So you don't have to worry about that. I'll show you the information sheet just now, just so you can check that. This one is on the information sheet. And we already discussed this in the previous video, where we said if the function is e to the power of x, then the derivative of that function is also going to be e to the power of x. And we discussed that in terms of tangents, where we said if you draw a tangent to the curve e to the power of x, then the gradient of the tangent is also going to be e to the power of x. So that is very, very, very much something you should remember, even though it is on the information sheet. Now the following is not on the information sheet. They're not always going to just have e to the power of x. Sometimes what they will have is they will have e to the power of another function. So that other function could be anything. It could be e to the power of 2x. It could be e to the power of x squared. It could be e to the power of bracket x squared minus 4x. The point is, the moment that e in its exponent position right there has another function, then we will have to use the chain rule. So using the chain rule, the first thing we have to realize is the outside function is the exponential function. So the derivative of that exponential function stays exactly the same. That doesn't change. But according to the chain rule, I then have to multiply by the derivative of that inside function. Now this is not on the formula sheet. The reason they don't put that on the formula sheet is because they expect you to understand the chain rule. So if you look at the formula sheet, sorry, there's a bit of a glare on there, you'll see we have that e to the power of x, e to the power of x. What we do not have is we do not have this e to the power of fx, which becomes e to the power of fx times f accent of x. Okay, that's directly from the chain rule. Okay, so very important. Now we're going to do a couple of examples, and these examples on page 71 and 72 of the textbook. At first, all they do is they say, given that f of x is equal to 2e to the power of x plus e to the power of negative 3x, please determine the derivative of that function. So if you look at the derivative of that function, you are going to find the derivative of the first term, and then you're going to find the derivative of the second term. Now the derivative of the first term is quite easy. And the reason it's so easy is because there's not really any complicated functions in that exponent position. So the derivative of 2e to the power of x is simply just 2e to the power of x. Now, by the way, some of you might ask, why don't we use the product rule there? Why don't we say it's 2 times e to the power of x? You can do that, but it is completely unnecessary. If you were to use the product rule there, the first thing you would do is find the derivative of 2. But the derivative of 2 is 0. So it's 0 times e to the power of x, which is just 0. Then you'd have to go and say plus the derivative of the second function, which is e to the power of x, times that first function, which is 2. And that is why if you have a constant function times another function, you don't generally use the product rule. You just go and you find the derivative of that second function. You never really go and find the derivative of the constant function, but specifically it's got to be a constant function. Now, this is the part we discussed up over here, where we said, if we have e to the power of, in this case, negative 3x, that negative 3x is then my inside function. Or, the way I wrote it up here, fx. So when we find the derivative of this, we first start by saying we don't make any changes to the outside function. The derivative of the outside function is still e to the power of negative 3x. But now I have to go and multiply by the derivative of that fx, the inside function, which is the negative 3. So I'm just going to clean this up slightly. It's going to be 2e to the power of x minus 3e to the power of negative 3x. And that is then the derivative of that particular function right there. Right, let's try another one. This one, unlike the previous one over here where I'd said, please don't use the product rule because it's a constant function times e to the power of x. This one is not the same thing. And the reason it's not the same thing is because in this particular one, I have x squared times e to the power of negative x. This is not a constant function. So right over there, I'm going to be using the product rule. So please remember, I'm going to be using the product rule. But right over there, I'm going to be using the chain rule. And that is simply because of the fact that you've got that inside function, which is negative x. So we find the derivative of fx, and we say, according to the product rule, it's first the derivative of x squared, which is 2x, times the second function. And the second function just stays the way it is. I don't make any changes to that second function. Plus. Now we're going to keep that first function the same. No changes to the first function, but I'm now going to multiply it by the derivative of the second function. So the derivative of the second function, first the outside function, which is e to the power of negative x, but then I have to find the derivative of that inside function. So that inside function is going to be negative 1. The derivative of negative x is negative 1. And then I'm going to clean everything up, and I'm going to say it's 2x times e to the power of negative x. And then this one's going to be minus x squared e to the power of negative x. So that's the derivative of that x squared e to the power of negative x, specifically here using your product rule. Okay, we're going to keep on going with these examples. They're all still on those pages 71 and 72. So the next one says, please find the derivative of fx equal to fx equal to e to the power of 2x divided by x. Now, this one specifically, you'll see, is my quotient rule. So right over there, I've got my quotient rule. And again, over here, right over there, I've got my chain rule. So we're going to find the derivative, saying the derivative is equal to, and first things first, we have to find the derivative of the numerator. So the derivative of the numerator using that chain rule is e to the power of 2x, which is the outside function, multiplied by 2, which is the derivative of 2x. So that's the derivative of that inside function, minus. Now we have to find the derivative of the denominator, which is 1, times just the numerator, which is then e to the power of 2x. Divided by the denominator, and we have to square that using that quotient rule. So again, I'm going to clean this up, and when I clean this up, I've got 2e to the power of 2x minus e to the power of 2x over x squared. And by the way, you should be able to see that these are in fact, I made a massive mistake here. Oh, apologies about this. I forgot. See? I don't have you guys to keep me honest, and because I don't have you guys to keep me honest, I'm making mistakes. So let me just correct that mistake. I'm sure Jared was probably already going like, ma'am, you made a mistake. So thank you for that, Jared. I'm sure you were doing that. So what I forgot about the quotient rule up here is the following. Yes, I was supposed to find the derivative of that numerator right there. But according to the quotient rule, I was also supposed to multiply there by the denominator, which is x. So that means I completely forgot about that quotient rule, which is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. So there is my mistake. My sincerest apologies, which means I'm now going to have to fix this up, especially for the OCD people. I will even use Tipix to make sure that I do not mess it up completely. So if I clean it, it's going to be 2x times e to the power of 2x minus e to the power of 2x over x squared. I will try my best not to make any more mistakes like this. But if I do make mistakes, please, people, put that in the comment section of the classroom mathematics. Okay, next one. The next one, we've got f of x is equal to 1 over the square root of 2e to the power of negative x plus 1. Now, I would first go and change this a little bit, and I would change it by making it 2e to the power of negative x plus 1, and make that to the power of negative a half. It just makes everything a little bit easier. So again, over here, I've got a chain rule over there, but then when I find the derivative of the inside function, I have another chain rule. So I have a chain rule inside a chain rule. So in order to find that derivative, f accent of x, we start by using the outside function first, which is going to be negative a half. Remember, don't touch that inside function yet. We're still just finding the derivative of the outside function. And then I have to make this exponent 1 less, which is minus 3 over 2. And then I have to multiply by the derivative of that inside function. Now, this is specifically where we use the chain rule. The chain rule is going to be that 2e to the power of negative x, which is the derivative of that outside function. But because this says negative x, I need to go and multiply by that negative 1, which is the derivative of the inside function. Now, the derivative of 1 is just 0, so there I am now done. And again, I'm just going to clean everything up a bit. In order to clean it up, I'm going to say I have negative a half there times negative 1. So negative times negative is positive, and obviously a half times 1 is a half, so I'm just going to put the 2 at the bottom here. And then I'm going to take that 2e to the power of negative x. Now, by the way, you could actually just go and leave it at the top. So you can leave it in the numerator 2e to the power of negative x. If you want to move that e to the power of x down and make it e to the power of negative x, that's also up to you. And I see as well here the 2 divides into the 2, so that means we're going to have to fix that one up as well. And then over here, I'm going to move this down. That is still a square root. I don't know if you've noticed, that's still a square root, so this is going to be a square root, but that one is still going to be to the power of 3. So I've got 2e to the power of negative x plus 1 to the power of 3. So a little bit messy. Let's just rewrite it properly to make sure you are all happy with this particular one. By the way, you'll see in the textbook, they actually just didn't even change the negative exponents, and they also didn't move it back into the surds. So in the textbook, they actually just went and said e to the power of negative x times 2e to the power of negative x plus 1, and they left that to the power of negative 3 over 2. So if you are perfectly happy with doing that one, I'm also perfectly happy with that. Especially if it's going to become a little bit messy, and especially if you're worried that you're going to mess up your exponents, I'd rather just have you go and do it like this. Okay, so hopefully you understood this one. I will keep going with the examples, and again, if you have any issues or problems, please people email me as soon as possible so we can sort it out before it causes any issues later on. Right, next example is number 2, equation of a tangent to the curve fx is equal to e to the power of 2x minus 3x at the y-intercept. So we are looking for a tangent to the curve at the y-intercept. So obviously we will have to first find the y-intercept. Logically speaking, at the y-intercept, my x coordinate is equal to 0. So I'm going to quickly first go and say, what is the f of 0? And that's going to be the y-intercept. And we have e times 2 e to the power of 2 times 0 minus 3 times 0, and that is just going to give me 1. And the reason it's going to give me 1, 2 times 0 is 0, e to the power of 0, or anything to the power of 0 is 1, and then obviously minus 3 times 0 is just going to be 0. So I know that the y-intercept is the point 0, 1, and I'll come back to that a little bit later. But in order to get the equation of a tangent, we need to get the gradient of the curve at that x is equal to 0. So in order to get the gradient of the curve where x is equal to 0, I need to find the derivative, because remember the derivative is the gradient function, so that will get us the gradient. So we're going to say the first derivative of this fx. Now first over there, watch that chain rule please, careful with that. So it's e to the power of 2x times 2, because the derivative of 2x is 2, minus 3. So that was pretty easy and straightforward. And now I need to go and I need to substitute 0 in there, which is the x coordinate at that y-intercept, and this is going to give me the gradient of the tangent. Okay, so the gradient of the tangent is then going to be 2e to the power of 2 times 0 minus 3. There we go. And this is then going to be 2 times 1, which is 2 minus 3, and that means the gradient of that tangent is going to be negative 1. And then remember the equation of a tangent is just a straight line. So I've got the gradient of the straight line, I've got the point of contact of that straight line, so I can then just sub it into my normal formula. Y minus 1 is equal to the gradient negative 1 times x minus 0. And that then means y is equal to minus x plus 1. And that is the equation of that tangent that I'm looking for. And according to the textbook, my answer is correct. I'm just going to keep myself honest as well, since you're not here to keep me honest. And I will just every now and again, once I've completed it, I will check the textbook. So if I do make a mistake, I will immediately try and fix it. Hopefully that won't take too much time in the video. Okay, right, next, number 3. Find the position and nature of any stationary points of the following function. And that function is y is equal to x minus 2 e to the power of negative x. So please, people, remember, the moment you see the word stationary points, right there, very, 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 very important. You have to remember stationary points means it's where my derivative dy over dx is equal to 0. That one, very, very important. You should not even think about that. That should be like second nature. Stationary points is where the derivative, which is the gradient, is equal to 0. Because that is where the curve is standing still. Even just for a split second, it's not increasing or decreasing. It's got a derivative or a gradient of 0. So in order to do that, I first need to find the derivative of that function. So I'm going to go and say dy over dx. And let's plan this derivative like we should every single derivative. We say it's a function x minus 2 times another function e to the power of negative x. So that's going to be product rule for us. So I'm going to go and use the product rule, which says first find the derivative of x minus 2, which is then 1, times the second function, which is just e to the power of negative x, plus. Now I need to find the derivative of that particular function, which is e to the power of negative x times the derivative of the inside function, because this is of course a chain rule again. So because it's a chain rule, I say the derivative of that negative x is then negative 1. That is going to annoy me, sorry. Let's just fix that, otherwise you guys are going to wonder what's going on over there. Right, and then to finish the product rule, I still need to multiply by that function. So x minus 2. So let's check that again. Product rule. That is the first function, that is the second function. So I find the derivative of x minus 2, which is 1, times the second function, no changes there. Then I find the derivative of the second function, which is e to the power of negative x, and then I have to multiply by that inside function's derivative, which is negative 1, and then this one I just multiply to finish the product rule. Now I set all of that equal to 0, and please people, do not forget that equal to 0. They actually penalize you in the final exam if you don't make sure to make that derivative equal to 0. Because if you don't set that equal to 0, then you don't actually have an equation which you can solve. So I see lots of people not do the 0, they simplify that, and then somewhere during the course, they suddenly have an equation which they solve. Please people, this is actually important. I'm going to highlight that to remind you it is important to have that equal to 0. You get a mark for that in the memo. Okay, so I'm just going to clean this up a little bit. It's e to the power of negative x. And then this one specifically is then minus that x minus 2 times e to the power of negative x. Now, please, people, I know this is a very strange equation. I mean, the first time you look at this, you're going to go like, I've got no clue. That's okay. Please don't worry too much. But normally what we do, we are so used to solving polynomial equations where we factorize that hopefully you guys should spot that common factor of e to the power of negative x. So I'm going to go and I'm going to take e to the power of negative x out as a common factor, which is then going to leave me here with 1 minus x minus 2. I'll clean that up just now. So if you look at it, you'll realize I've got the first factor, e to the power of negative x equal to 0. So e to the power of negative x is equal to 0. Or over there, I've got 1 minus x plus 2 is equal to 0. So this one will then give me minus x is equal to ln of 0. And hopefully you guys should immediately realize this can't happen. I can't have a 0 there. Besides, before you even did that, you should have realized this is not possible. It's impossible to have an exponent here that will make a base of 2,718 equal to 0. So that immediately makes no mathematical sense. But if you did go and change it to the ln of 0, you would have realized the moment you typed it into your calculator, so if I turn the calculator on and I say the ln of 0, it's a math error because there's no such thing. Okay. Then over here, we can then go and say, okay, so x is then equal to 3. Oops, making lots of mistakes today. This is going to be fun. There we go. So x is then equal to 3, which then means this is my stationary point. Now I also need to go and need to look at the nature of that particular stationary point. By the way, they didn't ask for the coordinates of the stationary point, but generally what we do is, unless they only say, please find the x coordinates of the stationary point, we have to get into the habit of always subbing that back into this to get the y coordinates. So let's do that before we look at the nature of the stationary points. So we say y is equal to 3 minus 2 times e to the power of negative 3. And you'll see that then simplifies to 1 over e to the power of 3, which means the coordinates, the proper coordinates of the stationary point is 3, 1 over e to the power of 3. There we go. Okay, now to look at the nature of the stationary points, I'm again just going to look at my first derivative table. So you should be used to that first derivative table by now, where we say there is my x and there is my derivative, dy over dx. Okay, and we said the x value of that stationary point is 3. So I'm going to look just before, which is the point 2, and just after, which is the point 4. And I'm going to just use my calculator, my table function. So I'm going to set this up going mode 7, and then I'm going to type in that simplified version over here. Well, I suppose you could use this version or you could use this version. You can even use this version. It really doesn't matter. Just the idea is that you need to take one of these versions of that derivative so I can look at what happens with the derivative. So let's use this one since it's the simplest one to type in. So I'm going to go e to the power of negative x and then times 1 minus x minus 2. There we go. And then I'm going to start at 2. I'm going to end at 4. And I'm going to step in 1. Now, this then takes me back to this particular table. And on the table, you should be able to see, I hope you can see this, where x is equal to 2, my derivative function, or my derivative, or my gradient is positive. Then 0, which I expected, and then it's negative. So I can just make this, and I can say it's positive, 0, and then negative. And you guys should realize by now, if the gradient goes from a positive to a 0 to a negative, then what we have here is we have a maximum turning point. So always remember to not only do the table, also remember to write down your deduction. So this point that I worked out there, that stationary point, is a maximum turning point because the gradient goes from positive to 0 to negative, so that's a maximum turning point. Now, just for interest's sake, you can actually go and you can look up this function on Geogebra. So I've drawn this function on Geogebra. It's quite an interesting function. It looks like this. Sorry about that little bit of a glare. Hopefully it won't obstruct the view over here. Now, if you look at it, it doesn't actually seem to have a turning point. You look at it and you go like, there's no turning point there. But what you should notice here is this thing this graph does. It goes up, 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 and then suddenly it looks like it goes down. So I'm just going to zoom in a little bit over here so you guys can hopefully see what's happening. And I'm going to try and do it only on this axis because this is the more important one. I hate it when I'm having technical difficulties. Okay, that's better. Ah, that looks a little bit better. So if I do that, you guys should be able to see the graph is increasing, going up, 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 and there at 3, it reaches a maximum turning point, and then it goes down, down, down. So yes, it's definitely a maximum turning point on that graph there. Great, so that was then all of the examples in the textbook on the derivative of e to the power of x. We need to now move on to the derivative of the log function. Now this derivative of the log function, I'm going to stop the video right here because we're already on about 25 minutes. So I'm going to stop the video right there, and I will then go and I will continue the video saying that the previous video was part 1 and this particular video is part 2. So see you in the next video.